I'm from NICT Japan. And the title of my talk is Advances in Natural Language Generation for Indian Languages. First of all, thank you very much for having me give this talk. It allowed me to put together a bunch of stuff I've been working on recently into one coherent presentation. It was a nice opportunity. So a little bit about myself. I'm a researcher in NICT Japan, and I'm an adjunct faculty at IIT Madras. Actually, Varun was one of my mentees at IIT Madras when he was in AIFA Bharat. I'm also a visiting researcher at IIT Bombay. Back before NICT, I was doing my PhD in Kyoto University, and then before that, I was a MTech student in IIT Bombay under the guidance of Pushpak Bhattacharya. As far as my research goes, I've been focusing on multilingual machine and speech translation since quite a long time ago. Then a bit more recently, I've been dabbling with document level machine translation. My speech translation experience is a bit more recent, but I'm trying to build a lot more on top of it. I've also been dealing with large scale pre-training for generation since 2021. And again, from my PhD days, the final part of my PhD days, I've also been focusing on compact, flexible, and fast models. Before I get into the talk, I'd like you to, feel free to stop me and ask me any questions, or if you prefer, at the end, you can ask me any questions. That's totally fine. So what is natural language generation? Natural language generation, we already know, it means generating in any natural language. We have tasks like translation, paraphrasing, summarization, and question generation. For translation, it's like, okay, you put an input in one language and you want the translation output in another language. Paraphrasing, which means just rephrasing something. Summarization, which means compressing content from maybe long form into short form. And then question generation is more like, is the opposite of question answering, where you state something and then you make the model ask a question. It's like, it's like a game. It's trying to check if the model is able to understand the answer and then figure out what might be the question relevant to that particular answer. So what are the challenges over here? There are data challenges, there are modeling challenges, and the solutions are typically data mining and pre-training. So back in 2021, when there was almost no work, one of the first questions was, why do we even care about Indian languages? Well, the reason is because there are 4 language families, 22 scheduled languages, 125 million English speakers, and 8 of these languages are in the world's top 20 languages, and 30 of these have more than 1 million speakers. And if you look at the right side, the plot tells you the how much internet usage has increased in India. You can see that in 2011 it was barely 100 million users, but now we have in 2021 it was 735 million users. So it's just gone completely out of control. In 2024, as far as my reading goes, it's about 800 million, but that number is just going to shoot beyond a billion in a couple of years for sure. So that means now that there are internet users who use Indian languages exploding on the internet, it means that we definitely need technologies for Indian languages. It's the need of the hour. So what was missing? Of course, we have data, pre-train and retrain models, the data specific for natural language generation, and then the models themselves and evaluation of these models. So in this talk, I'll be focusing on the foundations that we worked on in the form of IndicBART and IndicNLG benchmark. Then I'll go into 2 aspects. One is how we further try to solve the data problem, because when we did our foundational work, we realized that there's actually a lot more work to be done in terms of data as well as modeling. So I'll be focusing on how we 2 works that focused on solving the data problem, which is the Indic LLM suite and using synthetic data or translationese. And then the modeling part, where we worked initially on this model called Airavat, and then on a more recent work called Roman Setu. So what happened when we started our NLG journey? We realized that there is very little or almost no supervised data. So the solution that people typically use when you have very little amount of supervised data is to perform pre-training on a large monolingual data. We are in the LLM world, so this is fairly obvious, but back then it wasn't that obvious. So what we did was we trained what is known as the IndicBART model, which is an encoder-decoder model for the top 11 Indian languages, top 11 in terms of number of speakers as well as availability of data. So we had the IndicCorp data, which is currently pretty old, and it has been superseded by other data sets like Indic LLM suite and so on. But at that point of time, this was the only thing that was available. And the one important thing that we did was to map all the scripts of the other languages into Devanagari. Why? Because Indian languages are very similar, and by mapping everything into Devanagari, you have the opportunity to exploit a lot of overlapping vocabulary or subwords. The next thing is to train by text infilling based objective, where you also have the option of sharing the layers between encoder and decoder. Why? Because you kind of also want to have efficient models, models that have fewer parameters but have the same performance as larger models. And as a result, we have different types of models where we have unified script IndicBART, you have separate script IndicBART, and then this model called as IndicALBART, which is never really popularized, but it is a very useful model called as unified script IndicALBART. Now, these models are very tiny, 97 million parameters to 244 million parameters. And when you compare them to existing models like MBART at that point of time, which had 611 million parameters, these models were quite compact and focused specifically on Indian languages. Also, the data that we trained on was rather small, but as you'll see, the results were pretty interesting. So,
Hi Raj, one
yes,
sec. Yeah.
yes,
Can you go back to the previous slide?
yeah.
Can you explain the third process, the text infilling training? Like what exactly were you
I'm
doing
getting to
here?
it. I'm getting to it.
Okay, cool.
Yeah. So what is script unification? Again, as I said, it's an opportunity for you to share vocabulary and reduce the need for very large vocabulary. So if you look at these two sentences, they are in two South Indian languages. I don't know whether they're Tamil or Telugu, which one is which. But if you convert everything into Devanagari, then you can see, okay, there is a certain amount of similarity that kind of appears between the two languages. And if you train a vocabulary on these, shared vocabulary or shared script equivalents of the original scripts, then you have the opportunity to kind of share a significant amount of vocabulary. And when you share some vocabulary, you always have the opportunity to perform some kind of transfer learning. So what is infilling? That is a question that was asked. So you have this thing called as this sentence, suppose, mujhe mask pasand hai. You want the model to predict a completion, like is replace this word, this mask with a particular word. So one replacement for the word mask would be bhashantar, which means I love translation. On the other hand, it's not just words that you'll be replacing, but you can replace entire phrases, like I mask would be replaced by I love translation. So you can have not just words, but entire phrases being replaced. So this is just very standard naive approach. Ever since then, there have been more advanced approaches like UL2 and so on. So I recommend that you read up on this paper called as mixture of denoisers. I think it was released in 2022. It's a very interesting read, and it kind of builds on top of all these infilling based objectives. So, of course, once you do pre-training, you have to find.
Raj,
Yes.
I think there was one question. Arun had a question.
Yeah.
Hey, hi, Raj.
Hi.
I have a question on the vocabulary part.
Yes.
So I understand that sharing vocabulary can improve the chances of transfer across languages, but it could also mix things, right? For you, for example, the word paiyan in the different language may not have any sensible meaning at all, versus it has specific meaning in Tamil language. Now, are you handling that in some way? Do you see that it needs to be handled at all, or you don't need that doesn't need to be handled at all?
Right. So not explicitly, we don't handle it. And if you look at it, actually, as long as there is context, the model is able to differentiate between different things. So it often happens that there is a huge amount of overloading on certain tokens, but models are clever enough to figure out, given a context, what is the true meaning of this word. So there are pros and cons to this, and there are certain approaches that people have proposed in order to provide some additional information in terms of features or language indicators and language tags. But it turns out that context is more or less enough to solve this issue.
I see.
Yeah. Cool. Okay, so you've pre-trained your models. The next step is, of course, to fine-tune it. And we evaluated on machine translation as well as summarization, but due to lack of time, I'm just going to focus on machine translation. And if you can look at the plot on the right side, you see Indic to English and English to Indic machine translation. And we have this model trained on Scratch, which is in blue. We have this MBART model, MBART 50, which has been fine-tuned. And then we have the IndicBART model, which is about a third of the size of MBART and which has also been fine-tuned. And you can see that in all the cases, it is beating the EMBART 50 model consistently despite being smaller. Why? Because this model is dedicated for Indian languages. It has seen more Indian languages content, and it is specifically optimizing certain characteristics in terms of vocabulary and transfer for Indian languages. So it means having this dedicated model for Indian languages is definitely one of the ways to go. And this behavior is seen consistently both for the forward as well as the reverse translation direction. So what happens when you go down and look at this IndicNLG model? The IndicNLG model is 97 million parameters compared to IndicBART's 244 million parameters. And what happens is that, of course, because you've cut down the number of parameters, you do lose the performance. You go for Indic to English performance from 30.66 to 28.83 as measured by Blue. That is to be expected. You do drop in performance. But what happens if you distill from this IndicBART model to the IndicNLG model? Well, it turns out that you can recover a majority of the performance and have performance on par with the original IndicBART model. So we found out that if you have compact models, you definitely should be using some form of distillation in order to recover a significant portion of the drop. So these are some very tried and tested solutions, and they always more or less work out very nicely. So once we knew that, okay, there's this pre-trained model which can kind of solve this scarcity of data problem, we wanted to evaluate on other natural language generation benchmarks. And for that, first we needed to create data sets. So we came up with the IndicNLG benchmark in 2022, and this was a natural language generation data set for 11 languages and 5 tasks. We created about 8.5 million plus examples overall. So it doesn't look that low resource, but at an individual language level, it's pretty low resource compared to English data sets, for example. And we showed that language family specific pre-trained models are better than generic ones. I'll get to the results soon. And we show that our models are 3 times smaller, but competitive with larger models. So what are those NLG tasks? One is biography generation. So given some kind of a table, let's say from Wikipedia, you kind of want to generate a sentence explaining this particular biography of a specific person or any entity in general. There is headline generation, simple. You have a newspaper article, you want to generate a headline for that article. You have sentence summarization, where you have a long sentence and you kind of want to compress it by capturing only the essence of what is being said. And finally, we have paraphrase generation. You know what paraphrasing is. I don't need to elaborate here. And also question generation, where the input is an answer and the output is a question. You reverse it and it becomes question answering. Most of this stuff we obtained by either pivoting existing parallel corpora or by using back then IndicTrans in order to translate English-only datasets. Translating English-only datasets is a very common approach, and it will come up again and again in the next works that I'm going to be talking about. But yeah, in general, translation has become the go-to for solving a majority of the data bottlenecks that people have. So what happens when you fine-tune models for these energy tasks? You can see that you have the IndicBART model at 0.24 billion or 244 million parameters. And this 32.5 just represents a cumulative score, blue scores, rouge scores, and so on. And when we have no pre-training done, and the same number of parameters, we have a certain performance at 32.5. But when we have pre-training done with IndicBART and monolingual corpora, the score jumps from 32.5 to 37.7. What happens when you have a comparable non-language specific model like MT5? Well, you have 37.1, which is close to 37.7, but it turns out that, since IndicBART is more language specific and pretty compact, this is the model that you want to focus on. If you probably wanted to evaluate a bit deeper, it's likely that the language family specific model will have more advantages as compared to a generic model. And these are some numeric results, but in general, the conclusion is that pre-training really helps overcome a significant bottleneck for the fine-tuning data requirement. And then these language family specific models are competitive or better than generic pre-trained models. So
I guess Sanjit has a question here.
Yes.
Just one question, Raj. Did you guys also do a human evaluations, maybe taking some samples out and getting it evaluated from native speakers and also?
Yes. So we actually did do some human evaluation for some content from question generation and some content from biography generation. And we found out that most of the people had a reasonable inter-annotator agreement, and they all agreed that the data is not perfect, but it is usable. So they said that, okay, ideally we would want this data created by human beings as much as possible, and crawling does have its risks, but they said like, okay, it's usable. Like if between a choice of not having data and having data, it's better to have this data than nothing.
Makes sense. Got it. Thank you.
Right. Okay, cool. So these were small but meaningful efforts, and we wanted to kind of build on top of that. So what were the lessons? We have a low resource problem, and there are two solutions. One is the data solution, which is to inflate via mining and machine translation. And the second is the model solution, which is to have efficient models and enable as much transfer learning as possible. So now I'm going to get into the works that we did to address both of these types of solutions. So first, with the data solution, is when you don't have data, what do? You just mine it from the web. And the ideal solution, it is an ideal solution. Why? Because it means that people will be on the web. They will be, getting whatever true data distributions out on there. This kind of data will be free of model biases. It will be full of human biases, but not model biases. Problem is, this is exhausting because it involves verification, checking, and whatnot. And trust me, it's a nightmare. We tried doing it. The other thing is you can synthesize it. This is a non-ideal solution because it will contain model biases. But the advantage is that you can rapidly inflate from 0 to several hundreds of billions of tokens in a matter of a few weeks. And later you'll see that actually synthetic data is not that bad. So you have two options, and you kind of have to take a balance between them. So we came out with, yes.
So isn't it like right now when we scrap from the web?
Yes.
It's free. It's full of model biases because like most of the content, new content is being generated from ChatGPT and those kind of tools.
Yes.
So how we can work on that problem?
Good. That's actually a good question, and I'll address this 2 slides down. There is actually an answer over there. So, so in order to address this data requirement, we have the Indic LLM suite, where we built upon our previous learnings for Indic Corp V1 and V2, and came up with not just a pre-training data set, but also some instruction fine-tuning data set. But the question is, why would you even need such monolingual data? Well, the first thing is that we know that if you've played with ChatGPT, you know that if you ask any kind of questions to ChatGPT specifically, like, okay, where are the best places to visit around Yercaud? ChatGPT will give you this nice long yappy answer about, okay, details, points, and so on and so forth. But if you start asking ChatGPT questions in Hindi about the same thing, last time we checked, it didn't give a very satisfactory answer. It misses out on some content. So it means that these LLMs definitely have to see this kind of data during pre-training, and it has to see everything. Just because you've shown the data in English doesn't mean these models can actually leverage the same knowledge in another language. It is unable to do that. So therefore, we know that Indian people will likely ask questions on an Indic context. We want to have pre-training data that reflects this Indic context. And one more interesting thing is, even if you ask the question in English and you might think, okay, this data is already kind of in English, it might have been there. The model sometimes messes up even questions like how were Hanuman and Bhim related. In fact, they do have relation. They do have a relationship, but the model is not able to capture this. Therefore, we came up with the Indic LLM suite. The paper and data links are over here at the bottom. I'll send the slides later. So the Indic LLM suite consists of 2 major parts. One is Sangraha and then Indic Align. Sangraha is the largest collection so far of monolingual documents for 22 Indian languages. The figure just tells you an overview of what's what, but I'll get into specific details over time. So the other part is Indic Align, which consists of instruct information as well as some toxicity data information. And we all know that we want to have LLMs which are able to follow instructions, but should not be following toxic instructions or toxic content generation based instructions. So that's why we created both types of data, both types of alignment data sets. So how did we create Sangraha? Well, first of all, we had a lot of PDFs coming from Internet Archive, and we just passed it through an OCR engine. It was Google's OCR engine. We tried with some other things which were open source, but it didn't work out. So at the end of the day, we had to burn a bit of money and get OCR done. And as a result, we were able to get 14.5 billion tokens for a variety of Indian languages. The second option was, of course, web scraping. Now, this is that question, right? How would you know whether content has been generated by ChatGPT or any LLMs? So for web scraping, one solution is that you can try to use verified sources of data. So for example, if you know certain newspaper websites where the articles are known to be manually curated or manually written or written with some assistance from LLMs, but edited and heavily checked, then that forms a verified source. And when you have verified sources, do need manual intervention to check whether, okay, are these websites truly looking very good, or do they look like they've been just populated with content from some LLMs? So that is basically one of the solutions. Of course, it's very hard to detect what LLM content, but then there's watermarking and there are many other solutions. It becomes a chicken and egg problem, but at the end of the day, synthetic data is not all that bad, and we'll see why it's not that bad when I get to it later. So there will be some model biases, but at least this web checking, this verification process will help you eliminate a certain amount of bias. And of course, because of web scraping, we get 48 billion tokens. We have ASR, which means we have a lot of videos from lectures, from your index subtitles, like you have your movies and so on and so forth, open subtitles and so on. So there is a lot of audio data, and you can perform ASR from over there. And we got about 1.2 billion tokens, and for this we use the Hindi conformer model. Now that we've gotten a lot of this text data, we want to make sure that it's very clean. And for this, one of our residents at IndicBART, Priyam, he worked on creating the Setu pipeline. Essentially, it's a very large scalable pipeline for data extraction, cleaning and analysis, filtering, and deduplication. Deduplication, because redundant data is just a waste of compute. We kind of don't want that. And after going through all of these different stages of processing, you can get the data set, which is called Sangraha. Now, mind you that all of these processes are very standard, well-established practices. If you take a look at the Gopher paper or the Chinchilla papers, they'll give you more details on how this is. Even the Llama papers will contain details on these cleaning things. Just that we now have something specific for Indian languages, which is very scalable. So if you want, you can check it out. So there are two other parts to Sangraha, which is Sangraha synthetic and Sangraha unverified. And for this, we simply use machine translation and transliteration. So we used IndicTrans2 for bulk translation, and we use IndicXLit for bulk transliteration. So we took English Wikimedia and translated it to the 22 Indic languages from English to Indic using the English to Indic model. And we came up with 90 billion tokens. And then this translated content, some part of it, we transliterated, and we ended up with 72 billion transliterated tokens. So when I say transliterate, I mean we've romanized it. We converted all the scripts into, let's say, Roman script. And why? Because we use a lot of our technologies. Most of the times when we communicate, when we type in our native languages, we don't necessarily type in the native script. Sometimes we end up typing in Roman script. Therefore, this is a very important use case which needs to be properly tackled and addressed. And the approach itself is very simple for translating documents. You split documents into sentences, you translate the sentences, and then you assemble. The caveat here is that document level phenomena may be lost. So we need better solutions, kind of an open area for figuring out what is a good way to translate entire documents. We also have the MADLAD and Cultura X data sets, which were incorporated. This is high quality data, but unverified, because we kind of are not able to verify at the scale whether these URLs, which are used to curate this data, whether they're reliable or they come from reliable sources or not. Nevertheless, we have 24 billion free tokens. We just use it. So as a result, we end up with roughly 200 plus billion tokens spanning 22 Indian languages and English. So it is pretty comprehensive, and it covers a lot of languages and roughly a lot of domains as well. So now that you have pre-training data, you also need instruction data. So we also created instruction data focusing on a variety of sources. We have the IndoWordNet. In IndoWordNet, you have glosses, synonyms, cross-linkages. So if you have the gloss for a particular word, you can create an instruction. Given this word, can you write a sentence using this particular word or explaining this particular word? So you have free instruction data. Of course, this is at a syntactic level. It's basic, but it is very useful. You can at least teach the model certain basic concepts this way. And over 18 languages, it's 74 million pairs. You have to be very careful about over-representing this data. Otherwise, your model will end up focusing too much on this. So be careful about using this. The other types of data is Dolly, Open Assistant, and WikiHow. And we have 14 languages and 80,000 pairs. We have LLM generated content, which is context grounded QA pairs. If you look at the figure on the right, we essentially have LLMs, which we have told these LLMs, okay, limit yourself to specific topics. So we use Wikipedia, we use articles from Wikipedia, and we tell the model that, okay, this is the context of the following conversation. So stick to this specific context. So for example, we ask the model that, okay, the intent will be understanding the history of Delhi. And then we ask the LLM itself, okay, generate a specific question. Then we have another LLM or the same LLM answering specific questions and having turns in conversing with itself or with each other. And this way we have questions and answers grounded in specific context based on Wikipedia itself. And this kind of allows us to generate what is called as LLM generated information. And then we have the human in the loop, where human beings themselves provide prompts, provide questions, and then they interact with LLMs in order to create a conversation data set. So overall, we have a variety of data sets spanning, different kinds of use cases. Some of these ready-made, some of the data sets we made by involving LLMs. And once we've gotten all the data from, let's say, the English LLMs, we just perform translate test, and we perform translation and transliteration. And that kind of gives us a huge amount of instruction data. But I've also mentioned that we have toxicity
One
data.
question, Raj, sorry,
Yes.
on the previous slide. So
Yes.
with respect to translate, like again, like this is the problem that I have also faced while specifically using NMT model / Google API style translation. Like the problem of translation is basically like, semantic meanings of the sentences in the target languages are sometimes not, represented well. So while you were doing this exercise of both translate and transliterate, like you guys have also might have faced that problem, right? So did you do anything else post translation, or maybe use bigger LMs to avoid, or reduce the problem of translate? Or in your final models, did you see that some kind of robotic translations or robotic answers that are not colloquially sounding well in a target language? So yeah.
Yeah, so the problem is that because we were focused on scale, we didn't necessarily have the time to actually evaluate small specific use cases. But that is an
Okay.
ongoing area of investigation at the moment. How to ensure that there is none of this monotonicity and loss of semantic information. Mind you that the data was first generated in English via large LLMs and then translated. So of course we will be losing document level phenomena. I've mentioned this, that translation loses document level phenomena, but because we don't have reliable MT models which work at the document level. So that is actually an open area of investigation. But that being said, synthetic data, well, there is a follow-up work which I'll talk about in a few slides down. It does show you that even though this issue might exist, if you kind of scale it up properly, it stops being a concern. Maybe user satisfaction won't be that high, but it at least solves the bottleneck of limitation of data.
Got it. Got it.
I had a basic question. So
yeah,
when you're talking about like pairs, you're talking about question answer pairs that are
generated. Yes.
And one more thing, like when you're translating these into like a local language, how what are you using to do that translation?
So we're using IndicTrans too.
Okay.
Is that okay?
Yeah.
Okay, cool. Okay, so we need toxicity handling capabilities also. Well, essentially, we want the model to refuse to answer toxic questions, or at least give non-toxic responses, or giving some ensuring that, okay, if a particular question seems to be toxic, how do you answer the question without making sure that you aren't explaining to someone how to create a bomb, even if they ask how to create a bomb. So first of all, we had a taxonomy, which was created by Safi. He's another AI resident at AIFA Bharat. And we use this taxonomy to construct prompt templates. And then we use the kind of, let's say, unsafe model like Mistral 7B chat to create toxic prompts. So essentially, these will be prompts which might be toxic in nature, which might be asking something like, okay, how do you create a bomb, or how do you kill someone? How do you dispose of a corpse, and so on and so forth. So we had 126.7K prompts in English, of course. And then we have the HHRLHF data set, which consists of 169,000 prompts. And we pass it through a toxic classification stage, where you know that llama 270 billion is very, very, let's say, toxic proof. It knows how to, it often refuses to answer questions if there is some toxicity possibility over there. So we pass everything to the llama model. If the llama model says that, okay, I refuse to answer, or this seems to be something dangerous, then we consider this to be toxic data. And then we have a human aspect, which is from the HHRLHF version, which is a filtered down version of 32.7K prompt response pairs. And then from the toxic prompt generation taxonomy part, we have 90K prompt response pairs. So we have the human version, we have the synthetic version, and then we just translate this to 14 Indic languages, which we found to be very good for translation quality. We tried for the lower ended languages, but it turns out the translation quality was not that enough to get very reliable data. So we didn't proceed with that. And this gives us the Indic line toxic. So the next step is to build an LLM. We didn't do that actually because it takes a lot of compute and takes a lot of time. So we want to understand that given this data and what are the other things that we want to do to make sure that this data is actually reliable. So one important point that stood out was synthetic data, and we need to study how it is to be used. So speaking of synthetic data, how good is it? First of all, the questions will be, can synthetic data truly be useful for LLMs? Is cleaning needed? And how do we verify the impact of synthetic data? And this is where tiny LLMs and translationese data will actually kind of help you. This work was done with Meet Doshi of IIT Bombay. And this is one work that I'm really very happy and interested in, because it kind of answers a lot of interesting questions about the utility of machine translation. Like, you might hear people saying that, okay, machine translation is kind of saturated, it's kind of dead. But to me, it is a very important tool, and it is very important to improve it because it can still have major impact when it comes to LLMs and when it comes to data scarce situations. So why translation and tiny LLMs? Because translation is cheap, it's easy, it enables mass production, and it is somewhat reliable. As we've gone from IndicTrans 1 to IndicTrans 2, we've seen a significant improvement in translation quality, and the reliability and user satisfaction has also increased substantially. And why tiny LMs or baby LMs is because they provide a kind of sandbox mode to understand what exactly is happening in the language modeling phenomena, and it allows us to do large scale experiments. Once we do large scale experiments on a variety of scales of models, we kind of can do extrapolation and figure out what this kind of behavior would be at scale. Oh, there's a typo here, I'm so sorry. And it's very nice because it's low compute. 60 to 100 million parameter models on 6 billion tokens take less than a day on a single A100 GPU. And if you use libraries like Tiny Llama, you can do this blazingly fast. So you can actually verify a number of your hypotheses regarding your data and modeling choices on tiny LMs. So if you're not doing tiny LMs or small language models, I strongly recommend you read up more and try to get into this. It's very fun and very exciting. In our work, we specifically focused on 28 to 85 million parameter models and around 6 to 10 billion tokens worth of training data. So the overview is very simple. You have clean monolingual documents in high resource language, let's say for English. You translate at mass, and you have something called as unfiltered translationese documents in the target language. Now, we are not sure whether this unfiltered data is very reliable or not. How do you know whether a model is reliable or not? Well, why don't we just take the help of a small language model? So we again have clean monolingual documents in the low resource language. We might not have a lot, but we'll have something. We train a very tiny LM on that particular target language. Then we pass the unfiltered data through a perplexity filter using this tiny LM. And then we have this filtered version of the translationist documents. We rank them according to perplexity and take the top K representing a certain billion number of tokens. And then we use this particular translationist data and train a language model. And this is how we get a language model in the target language. Now, is this really useful though? And you might be interested in this because it turns out, yes, it is pretty useful. So if you look at this first row, it tells you what happens when you train a model on clean Hindi data. And you can see across NLU and NLG tasks, you have a certain performance where if you look at the average numbers, it's 77.60 for NLU and 32.0 for NLG. When you take unfiltered data of the same exact amount as Hindi clean, and you train a model and then fine tune it for the downstream tasks, you end up getting a significantly drop in performance to 74.26. For NLG, the drop is not that pronounced, but it is still there because you still average it over a number of tasks. So kind of see that, okay, unfiltered data is not that very reliable. Now, what would happen if you fine-tuned this unfiltered data trained model on some 10% clean data? So you take 10% of this clean data and you fine-tune this model over here. Turns out you can recover a significant amount of the performance. You go from 74.26 to 75.67. We didn't have time to do the NLG experiments, unfortunately. But then if clean data does have its value, then what happens with filtered version? So you take synthetic data filtered, that suddenly you have a huge gain in performance, and compared to 77.60, you're at 76.63, which has pretty much caught up to it. So it means that synthetic data itself, maybe for NLU it's not that viable, but NLG it's actually reasonable. And when you perform filtering, you don't see that majority of gains, but it does exist in a specific collection of tasks. So there is a huge amount of viability to synthetic data if you filter it properly. And then if you continue training on some clean data, even a small amount, you kind of get performance which approaches, if not, it's pretty good. It approaches the ideal situation of very high clean data. So it means now you're pretty much free to expand your data as much as possible and just go crazy over here. So this was results on Hindi. What about results on Gujarati? The same trend follows. You actually have, in case of Gujarati, the synthetic clean data version fine-tuned on some 10% of original clean data. And you see that this performance actually surpasses the performance of the model which has been trained on Gujarati clean data. And this is present in both the NLU as well as NLG situations. So finally, we have a very important finding over here, which says that unfiltered data does have its limitations, but you start filtering it and you start getting these really important and useful gains. So it would be very interesting to try, go into an area of research where you figure out what is the best way to get rid of bad translated data and retain only good translated data. We use baby LMs, tiny LMs as a use case, but there might be better approaches. So what about English only models? So for example, I've tried taking English documents and translating them into Indian languages. But what if I take Indic documents and translate them into English? Can it fill the gap for English data, which is not present in an Indic context? Well, it turns out actually it can do something nice. So if you have English clean data and you have this NLU performance, then if you take a, synthetic English data generated using Hindi, but not filtered, of course, you do have a drop in performance, which goes from 76.87 to 71.84. But the moment you start filtering that English data with a tiny LM or a baby LM trained on clean English data, you start recovering the performance. You go from 71.84 to 75.83. So essentially, the whole recipe of translating and then filtering using Perplexity, the way it worked for Indic language generation, it also works for English language generation as well as classification. So there is some important utility even for English data that has been generated. We also did some experiments on what happened with bilingual models, but because of lack of time, I'm not going to get into it. The key answer over here is that yes, synthetic data is viable, but you need to filter it properly. So the era of the synthetic data is upon us. It might be worthwhile to invest into this particular area. So we have a data solution, kind of. So what do we do next? We want to find out what is a good model solution. Any questions so far, by the way? Okay,
I think
one
small question. So like you have shown these results on mono by how, I think the next obvious problem is, can this be scaled to try or multilingual settings, and how the transfers happen, right?
Yes.
Got
Right.
it.
So that is the obvious question. The problem is that compute really hinders a lot. But the reason why we did these things was to validate our hypothesis that synthetic data has utility. And when we worked at two different scales at 28 million and 85 million, we found that the same trends were followed in both scales. We are fairly confident that this will carry upon larger scales as well. But again, we need a lot of compute to verify this. There are some ongoing experiments on Gemma 2 billion and Llama 7 billion using this synthetic data. And we are looking at some promising trends even at that scale. Maybe in a couple of weeks, we'll have that result and we'll put up an updated version of this paper.
That's great. Yeah. Thank you. Yeah.
Cool. Okay, cool. So now we want to get into the modeling solution. So let's go back to the question for what is the current case for Indian languages? Well, you have a semi-optimistic situation where you have a base LLM for only one language, but no instruction data. So which is this base LLM? It is OpenHathi, which is trained specifically for English and Hindi. and we want a solution for this. How do you get a LLM which follows instructions and does follow a variety of tasks in the native language, which is Hindi? And the outcome of this was the Airavat. We have the paper model and code. You can take a look at it. But this kind of base LLM might not always exist for all Indian languages. So what do you do in such a situation? You're in a bleak situation. So in this case, you have no choice but to rely on models like Llama 2 and more recently Llama 3. Llama 3 is a bit more multilingual than Llama 2, but it is still English majority. So that is an issue. Still, because you have no other choice, you need to figure out a way how to use these models. So the outcome of our investigation was this work called as Roman Setu. And this is again a very interesting piece of work that led to some very interesting real possibilities for utility of some transfer learning solutions, which are typically overlooked, but they really have very high utility when you actually put them in practice. So first I'll talk about Airavan. By the way, this was generated using DALL-E. Okay, so the data set that we used is currently right now a part of the Indic LLM suite, but what we wanted to go for was diversity and coverage. So we looked at FLAN v2, we had the Anthropic HHH, we have Dolly, we have Open Assistant, we have LMSys Chat, WikiHow, and Anudesh. Now, Anudesh was one of the things that we were creating at the time for Indic LLM suite. We also decided we wanted to test whether it was useful or not for any general instruct model, and therefore we kind of put it into practice for Airavat. And then NMT. Why NMT? Because any LLM should be able to handle machine translation as well. So we put all of this data together and then we mass translated it using our IndicTrans2 models. But we want to know if this data has very high, the translations have high fidelity or not. So essentially, sometimes it might happen, you put a sentence in English and it might hallucinate something in Hindi, which might not be related to the original sentence. So we did what is called as round trip translation, which means we translated from English to Hindi and then from Hindi back to English. And we compared the CHRF between the input and the input and the output and the original input. And we removed any, let's say, data which had a CHRF less than 50. So anything greater than 0.5, we kept it and we considered that as reliable data. So when you look at the filtered column over here, you can see that, okay, you do end up dropping a certain amount. You go from 67,000 to 65,000. You have 5,000 to 4,911. Okay, maybe a small drop, but it's still there. When it comes to WikiHow, we actually end up dropping a significant amount of data. So it is true that, you kind of end up having to drop out data. So cleaning is a very important part. We did some experiments on unfiltered versus filtered. We found out that filtered usually had better results, and unfiltered, despite being similar in performance to filtered, we considered that filter has much higher reliability because we could vouch for the content that would be generated. So how did we fine tune? We simply used LoRa. We also did full fine tuning, but found out that full fine tuning was not so viable. So we took LoRa, we fine tuned the model for 4 epochs. We used early stopping and checkpoint averaging. So what is checkpoint averaging? We evaluated the 4 checkpoints and we found out that the last 2 checkpoints were actually doing pretty well, neck and neck. So we decided to interpolate the weights of these 2 checkpoints using a weighing scheme of 0.6 and 0.4, where checkpoint 3 was actually doing a little bit better than checkpoint 4. And this actually ended up giving us a better model, which surpassed the performance of both these models. By the way, checkpoint averaging is not a very new thing. It was used back in 2017 with the Transformers paper. And in machine translation, it was a very big go-to technique to kind of do indirect ensampling. So yeah, it's something to look into for sure.
Raj, one more thing. How good is Dora when it comes to as a replacement to checkpoint averaging these days? Like,
so Dora, I have not played with Dora, so I'm not in a position to comment on this. I'm so sorry about that.
Okay. I think Sanchit also has a question.
I had one question. So this is like really simple. Like I think this is model merging, right? Like this has also come up quite recently. I've been reading about this. So like this is like I think one of the basic linear interpolation, and so I think there's a lot of I've also been thinking about this study. Like maybe model merging could be one direction to look into to build better models in that direction. Yeah, got it. Yeah, that's what it is. Interpolated rates and model merging. Yeah, I think. Yeah.
So model merging is one thing, but then there is a broader story over here. So you may have played around with LoRa, and you might have heard of something called as language adapters and task adapters.
Yes.
So
Yes.
this whole broad area of task vectors, task adapters, language adapters, model merging, which is kind of people do it pretty randomly, and there is some
Mhm.
theory that has been evolving, but there are still many more unanswered questions as to, okay, this works, but why would even model merging work? Like, what does the landscape, optimization landscape look like when you do this kind of model merging? So in machine learning, I've read only a couple of papers, but in the machine learning area, people have actually considered doing something called as, okay, you train, you do gradient descent on, like, say, case steps. Then you do a model merging of the result of those case steps to kind of having a moving averages kind of training. And that actually has an impact on your overall training, kind of gives you better gradient and model weight estimates as you train for longer. So this whole arithmetic of models is kind of very interesting area. If you want to go fully machine learning, it would be very cool to look at, I'm sure.
Yeah,
Cool.
thank you. Yeah.
Okay, cool. So let's look at the results. And essentially over here, we can see that there are 0 shot and 4 shot evaluations where we've done, and we found that LoRa is better than full fine tuning. 5 shot is not much better than 0 shot. Unfortunately, what happens is, when we compare, our models against Llama 2 7 billion with a translate test setting, or GPT-3 or GPT 3.5 and GPT-4, it turns out that these models are still far behind. Of course, GPT and Llama have seen a lot more data. Airawat has not seen that much, neither has OpenHathi. So the lesson over here is essentially that models do need to see a lot of data, and translated data sets need a lot of cleaning. There is some recent work by Gandhi. I've linked the paper in the slides. You might want to check on how they focus on getting high quality translated data sets or high quality synthetic data sets. So synthetic data set curation at scale and with quality is a very interesting open problem. Definitely recommend looking into this paper. So what if OpenHathi was not there though? What would we do? Well, nice thing is that Llama यह वाक्य समझ सकता है, and Llama can also understand this sentence. So what I've done is it's just in Hindi in Devanagari script and then a romanization. Turns out Llama can understand both of these things. You prompt the Llama model, it kind of ends up generating in both styles. So it means that inherently these models have seen a certain amount of romanized data. But why would that even be the case? Well, the internet is full of this kind of romanized data because we often type in romanized script. So that gives us a question. What do we do in such a situation when you already know that the model has a certain bias for romanization? So we came up with this approach called as Roman Setu, where we use romanization as a bridge between English information and the target language information. Oh my God, I forgot to do this. 1 second. Can I just move this here for once? Okay, let me continue. So why romanization is because, as I said, a significant part of web data is code, which is mixed and romanized. And what we did was a comparison of the fertility of native script representation as seen by Llama and the romanized equivalents. So we took Gujarati, Hindi, Malayalam, Marathi, and Tamil. We got it segmented by the Llama 2 tokenizer. And these are the average fertilities. That means the average number of subwords a particular word is segmented into, and then the romanized transliterated version of it, and what is the fertility for those words. And you can see there is a huge drop in the fertility. When you drop the fertility by this much, it means that in order to generate the same word, you would need a lot less compute when you use the romanized representation. So we basically had a very interesting finding where you know that, okay, if romanization has low fertility, and if the model can understand romanized content, then that might be the way to bridge the gap between the English performance and the native script performance, as well as the romanized performance. So how did we do that? We first had native script data. Sorry, I think 1 second. Okay, so we have native script data. We convert it into romanized version simply by using IndicXLit and the Anudesh data set. When we have romanized data, we first have to perform some kind of continual pre-training. Then we have supervised fine-tuned data, which we perform, which is present in English, but we translate it and then romanized it, and then perform instruction fine-tuning on top of the continual model. Note that you can just take the base LLM, which is Llama 2, and directly perform instruction tuning on the romanized equivalent. And at the end of the day, you have the fine-tuned model. So we have different possibilities, right? We have you can do continual pre-training on romanized data, continual pre-training on native data. You can do it on both. When you do fine tuning, again, SFT, where you can again do it on native romanized or a combination of both. And ideally, we should have a situation where the romanized performance should definitely be better than native. But in realistically, we want romanized performance that approaches the native script performance. So how does Llama 2 see romanization again? So one of the things that we did was we took the sentences in their native script version as well as in their romanized version. We also had their translations in English. Then we took the sequence vector of sentences as the last token representation of the last layer. And then we kind of figured out what is the similarity or cosine similarity between the sentences. So EN means you take an English sentence, its representation, and the native representation of its English translation in that specific language, and then compute the cosine similarity. So interestingly enough, if you look at the cosine similarity between English and native script representations of its translations, you have certain cosine similarities. But you look at the cosine similarities between the romanized equivalents, you get higher cosine similarities. It means that the model actually sees a higher degree of similarity between English sentences and their romanized equivalents in terms of translations. So that means it is very likely, it is a very good reason for why we believe that romanization might be a good bridging between the English representations and the target language representations. So the performance itself was pretty impressive, where we had the base LLM, which is Llama 2. We have just the CPT version or continually pre-trained version of that particular model, and then the instruction fine-tuned version of that CPT model. So you can see that for XX to English and English to XX translation, as well as Excel sum and Indic headline, which is summarization and headline generation, you can see that the romanized performance actually is able to match, if not beat, the performance of native script performance. Note that because of compute constraints, we couldn't generate native script content beyond a certain token limit, but romanized content could be generated for a fraction of that cost, and yet it's still matched, if not beat, the performance of native script performance. So essentially, it means that romanization is a reasonable alternative. CPT itself causes your performance to jump up significantly compared to the base LLM. In other words, the base LLM does need to be tuned with romanized or native script. But then if you do instruction fine tuning, you kind of shoot up in performance substantially. So essentially, yeah, it's a very simple solution. You take a LLM trained specifically for Indic languages, for English, you romanize the Indic content and just fine tune, you'll actually get a model. Of course, you do need to reverse transliterate the output, but that's a very small thing. It's a very simple thing. There are transliteration errors to be handled, but again, that's again an open question that could be addressed very easily. Now that we know that this works, you could consider taking Tamil data, converting it into Devanagari, and then fine-tuning OpenHathi on top of it. And that could be one other solution. So essentially, if you have an LLM in a given Indic language, convert every other Indic language to the script of that language, and then do instruction fine-tuning or continual pre-training. Or if you have nothing, just take Llama, perform romanization of all of your data, and do continual pre-training and fine-tuning. You'll still get a good solution. So overall, we found that by task, we have the CPT models as well as the instruction fine-tune models based on romanization, beating the base Llama performance, which is indicated by blue. And in terms of language-specific performance for 5 Indian languages that we worked around, our CPT and models based on romanization do give some of the best performance while also maintaining a low cost compared to native script performance. Now, mind you, native script performance is still good. It's not that it's not, but romanized performance has better cost benefits. So I recommend that. There are transliteration issues, but yeah, it can be solved, no problem. So in summary, I talked about some initial efforts for Indic natural language generation. I talked about IndicBART and the IndicNLG benchmark, identified certain limitations of the work where we found out that there is a data problem, which we solved using the Indic LLM suite and translationese based LLMs. Identified a model problem, which we solved via Airavat and addressed its limitations by Roman Setu. And in the future, personally, I'll be exploring the true impact of synthetic data and romanization. It's an ongoing work. I also want to think about what is a better and more reliable evaluation mechanism. And also, at the end of the day, of course, the dream is to have an Indic LLM which handles Indic relevant content. So that's the end of my talk. I'd like to thank all of my collaborators at Air for Bharat, IIT Bombay, as well as Anup, who is at Microsoft. So that's all for my talk. I'm happy to take any questions. Hello?
Yeah.
So
I think, is there any questions? Okay. I think
yeah.
Arun might. Okay.
Yeah. So hey, thanks for a great talk, Raj. The observation that we made, right, that Romanized script had better cosine similarity with the English sentence. That beyond the fact that it has seen a lot of Romanized data, how does one go about interpreting, right? So is it that these Romanized data co-occurred with the English set so that they are able to map the Romanized version of because the words are still uh, Balak or something like that, which is a Hindi word, which may be written in English script, but at the end of the day, it's a very different word. But the fact that there is a similarity between them uh, seems to be surprising in many ways, right? So any rationale, why do you think this kind of emerges? Even like, I don't know whether the proportion of this Romanized script is that high that it will be able to learn these associations very easily, right? So there is something more going on. Do you have a sense of what might be going on there?
So I have 2 points over here. The first point is that Llama 2 has majority seen 99% of the data is, let's say, in English. Nevertheless, if you start putting in some kind of Indic data, if you start asking it to translate from Hindi to English, it still does a good, somewhat decent job. So in other words, that data filtering is not very concrete. There is a certain leakage that is taking place. So if there is leakage taking place, there is definitely a leakage of code mix data, let's say English data, that has seeped through the entire filtering pipeline. And we know that there is a lot of code mixing on Twitter, there is a lot of code mixing on blogs and so on and so forth, and social media, of course. So I'm assuming that, and I'm not confident about this is conjecture, but Facebook does have access to, Llama might have access to Facebook data, and a significant portion of Facebook data would be code mixed as well. So if that is the case, maybe the model just has better enough representation. I mean, first of all, it's romanized, so subwords will be common. If subwords are common, already that kind of gives you a good basis for having similar representations. And then given the fact that it might have seen a lot of code mix data, it might be one of the reasons why it sees it as more similar to English. It might be coincidental, by the way. So that needs a bit more analysis, I feel.
Do you plan to do some analysis of that sort, like take more models and see whether this kind of phenomena emerges even in other models?
So we actually I've been looking for an intern to do that for quite some time, to take not just Llama but also Bloom and a lot of variety of multilingual models to do this analysis. There is this one paper which came out in early February or mid February, which analyzes what happens at different layers and how multilingualism emerges or is viewed by LLMs. I could probably send the link for that paper later, but yeah, it is an interesting area, I think.
Yeah,
I don't. I put that paper what Raj is talking about in the chat. What Raj is talking about. Yeah, you can have a look at it. Yeah, it's a pretty interesting paper. Like, which says like why Llama 2 specifically thinks in English. So a mechanistic overview of like how things pan out layer by layer.
I see.
Yeah, this paper is very interesting. If you haven't, I strongly recommend reading it. Kind of gave you some very interesting, it gives a very interesting insights. And it kind of tells us why, even if you find, so for example, when you have encoder only models, let's say you have XLMR, you fine tune on English, you can still get performance in other languages. But you take a decoder only model, you fine tune on English, you kind of lose performance for the other languages. It's because at the higher layers, the model ends up focusing only on specific languages and cannot concentrate on others. But at the lower layers or the intermediate layers, there's a lot more of multilingualism going on. So the whole transfer phenomena most likely has to take place over there, and that paper kind of exposes a very interesting possibility for that.
I see. Thank you. Thank you so much.
I think that should be it for the talk. I think we have almost run out of time. So thank you, Raj. Thank you for giving this talk. I know there's a significant time difference between India and Japan. So Yeah, do share the slides for this. We would like to actually have that resource with us, and it would be good to have all the slides and all the information you presented. Yeah, so that's all. This is the first session of our new reading group, and Raj was our first speaker. So thank you all for joining. We will have more sessions very soon.
Thank you.
Yeah.
Bye bye.
Yeah, bye.
Thank you. Bye bye.